Hello, everybody. My name is Matt McDowell. I'm an assistant professor in mechanical engineering and material science and engineering, a joint appointment here at Georgia Tech. I've been here for just about 4.5 years. And what my group works on is batteries. So each of you has multiple batteries in your lap or in front of you right now, of course, in your laptop, your cell phones. These batteries are lithium-ion batteries. And actually, this technology was just awarded the Nobel Prize in Chemistry, some of the inventors of this technology. So it's been, lithium-ion batteries have been key for the energy transformation and for mobility in our society. But there are a number of technologies that are going to be very important in the emerging energy, the way that we use energy, that cannot use lithium-ion batteries, because lithium-ion batteries have too little energy and are too expensive. So some of these technologies are electric airplanes, electric flight, and also energy storage on the grid. So to move towards these new technologies to enable new directions for our society, we need batteries that can hold more energy and that are cheaper. So it sounds relatively straightforward, maybe, but as a battery scientist, it's very challenging. One of the challenges is we have to move away from the materials that are inside the batteries that we're using now to new materials. And we have to make sure that these materials can last a long time as you charge and discharge your battery, and that they don't degrade over many hundreds and hundreds of cycles. So it's a big challenge. There's lots of people in many fields working on this from a variety of different angles. So I'll tell you what my group does. We have kind of a unique approach. So a battery is kind of a closed system. You've seen AA batteries, like your Duracell or your Energizer batteries. You know, it's just a little cylinder. You can hold it in your hand. These are quite similar in shape and size, actually, to the batteries that are found at a Tesla. So if we were to take a battery, we could plug it up to a current and voltage meter, and we can read out the current or voltage and maybe learn a little bit about what's going on inside the battery. But we don't actually know what's happening to the materials inside the battery as we charge and discharge. So my research group here at Georgia Tech, we build special types of battery cells, and we use various experiments to actually image and understand what's happening inside batteries down to the very atomic scale, very small length scales. So for instance, we use electron microscopy, where we actually shoot electrons through very small batteries and can understand how the materials are changing and evolving at the atomic scale during this process. We also use X-ray microscopy and other types of techniques, and we bring all these techniques together to get a much better idea of what's happening inside our batteries so that we can engineer the materials to work better, basically. So just to conclude, there's two main battery systems that we're working on for anybody that's interested. One of these is solid-state batteries. These are kind of an emerging battery system that could be safer and have higher energy than lithium-ion batteries. And then the other battery system that we're working on are metal-based batteries, so lithium and sodium metal-based batteries, which also could have higher energy. So that's a materials perspective, an engineer's perspective on batteries, and kind of how people here at Georgia Tech, my group and others as well, are taking a unique approach to understanding and engineering battery systems. And it's been really fun being here this morning, hearing about all the different research areas and other research groups are working on. And I think integrating some of the energy storage research here at Georgia Tech into the bigger picture, the smart cities, the grid scale type efforts, I think could be very interesting. So I'm happy to talk further here or elsewhere. Thank you very much.